So we'll start today's lecture. Today we'll be talking about the cleaning and the diffusion process. Cleaning is just like almost every one of you has done in the lab. And diffusion we have not discussed before, but part of the diffusion process we talked about in oxidation, if you remember. We'll be talking about the diffusion today and cleaning process. I see there is a homework number 3 for you people that is due by the next week. So that is regarding the cleaning process. So today we'll discuss about the cleaning and you can figure out the answers of these questions. So in cleaning, the first rule, that is AAA rule, as I told you in the lab, that you always add acid. Always add acid is a very important rule for the cleaning process. Whenever you have, you need to prepare a solution for cleaning, and you have one of that is acid, you always add acid. So acid always goes at the end of the process. So keep in mind that you never add something to the acid, but always add acid to the other chemicals. Okay, so there are actually two steps of cleaning process. One is named as FEOL, that is front end of line cleaning process, and the other one is named as back end of line cleaning, that is the front end of line and back end of line. As the name illustrates to a certain extent, that the front end of line means that starting from the silicon wafer to the process where the first metallic deposition comes into account. When you deposit the first metallic layer, when you make up the first electrical connections or first maybe a bonding wire or a metallic deposition. So before depositing the metallic layer on your device, the cleaning from the beginning to that step includes into the front end of line. And after the metallic deposition, the back end of line cleaning process starts actually. Okay, so it means that what we have, the cleaning process that we have done in the lab, that was front end of line process or the back end of line process? Sorry? So that was almost, of course, front end of line, because that we started with the silicon wafer and we did not have any metallic layer on the surface of the silicon wafer. So that's why we were able to use high reactive acids as well, high reactive alkalis as well, because we did not have any metallic layer on the surface of the silicon wafer. But in the front end of line, we use high reactive acids as well, just like Pranaclean. Pranaclean cannot be used in the back end of line process because that contains sulfuric acid, and if you have any metallic layer on the surface, sulfuric acid will actually get it dissolved. So that's why you need to be careful after you start the back end of cleaning process. After you deposit metallic layer, then you cannot use RCA process that we do use in case of a silicon wafer. Then you need to be careful that now we have the metallic layer, so we cannot use high reactive acids, the Pranaclean or the NH4OH or even HF cleanup process. You know about the cleanup process, that is actually the front end of line that we discuss in the lab. So I'm not going to talk about that front end of line process. So the back end of line process, in this case you can see that low reactivity solvents are used. Why low reactivity? Because I know that metal has been deposited on the silicon wafer, so I don't want my metal to get reacted with any of the high reactivity acid or base or something else. So low reactivity solvent. One of the most commonly used solvent is actually N-methyl pyrrolidone, that is named as NMP. That is most commonly used solvent in BEOL. Secondly, these solvents, those are actually low reactive solvents. They are not, the containers are not made of polyethylene plastic bottles that we usually see in the lab for the containers for the chemicals. For these low reactivity solvents, we should have either the quartz or the stainless steel containers for the low reactivity solvents. That's why it makes these solvents to be more cost effective, more costly as compared to the front end of line cleanup process. And secondly, So it makes highly expensive. And here we also talk about that in cleanup process, if we add some oxidizing agent or some highly reactive agent like oxygen or fullerene, the presence of oxygen fullerene also affects our cleaning rate actually. The faster it cleans, or we'll talk about later where when we'll be talking about the dry etching process. In the etch process, then you will come to know what is the effect of adding oxygen or what is the effect of adding fullerene to any chemical composition and how it will be affecting the etching process. Because cleaning is actually, you can say, a very slow rate etching. Cleaning is just like that you actually etch the surface. Specifically the oxide cleanup process, that is actually, if you etch silicon dioxide, that is the same process. You go for buffered hydrofluoric acid, BHF. And in the last step, that mostly the cleaning is actually just like you submerge your wafer in a board or in something in a solution that's named as a wet chemical cleaning process, but that has also been replaced by some other technique named as the vapor phase cleaning. In that case, actually, because you are spraying the chemical on the wafer surface, so you are actually consuming less amount of your chemical, so that makes it a more cost effective. So this is the this new technique is actually replacing the previous process. One example of back end of line cleanup process, that is a solvent clean. So in solvent cleanup, what we do, that first of all we clean it in acetone, then in IPA, or that is isopropyl alcohol, or maybe methanol, or even you can use all three of them as well. Then we rinse in DI water, then dry with nitrogen, so it removes the organics. If somebody out of you has been working with functionalizing the surface, means you are working with maybe DNA or RNA or some other things like that. So in that case, you have observed that for cleaning process, you follow this protocol. You always go for, you spray acetone, then you spray IPA, and then DA water. So mostly you repeat this process 2 to 3 times, so that you make sure that the surface is clean and you have not damaged anything. So they are not very high reactive chemicals that we are using. It's just an example of organic cleanup in back end of line process. Okay, as it discussed in the lab as well, that regarding the prana clean, that prana clean is mostly used for removing the photoresist residues, if you remember. The photoresist, the strips of photoresist that needs to be cleaned, this is one of the very critical step when you are cleaning. You need to make sure that there's no photoresist residues, because when you are fabricating a device, it may happen that you are spinning the photoresist, you're patterning your film, and again you need to pattern another layer of some other material. So you spin the photoresist again, and it may happen again and again. So that's why you need to make sure that before you deposit the next layer, you clean the surface and there's no photoresist residues from the previous photolithography process. So photoresist residues needs to be removed. When photoresist residues needs to be taken into consideration? After the etching process. So you know that whenever you etch some surface, it means that you are actually patterning the surface, because photolithography plus etching is actually one way of patterning a thin layer. You know, do you know about the lift-off process or no? Lift-off process. What is the lift-off? I guess because I was talking about the etching, so I believe when you know about photolithography and etching, you should know about the lift-off as well. When I say that photolithography plus etching.
In lift off, maybe photoresist was deposited.
It actually helps you pattern any thin layer, right? if you want to pattern a thin layer, you will have to do photolithography and then you go for etching process. So by using a photolithography, the exposed area would be etched away and the protected area that is protected by the photoresist, that would not be etched. So any thin layer can be patterned by using photolithography plus etching. At the same time, the same patterning can be done the other way, that is named as lift off. I believe when you will be talking about photolithography, Dr. Iqbal will discuss in detail what is lift off. But here, just to let you know that photolithography plus etching can do the same job what can be done by lift off process. So this process has its own benefits and lift off process has its own drawbacks. For example, lift off process can be done only for the metallic layers. If I need to pattern a metallic layer, I can go either of these two choices. But if I want to pattern an elastic layer, any elastic layer or polymeric layer, or that is not metallic, in that case, this lift off process cannot be used. Okay, anybody who knows what is a lift off? Because unless you don't know lift off, you won't understand why it cannot be used with elastic layers.
I think in lift off at first photoresist is deposited, then is etched, then the metal layer is deposited.
Yes, he is very right actually. That in lift off process, before the deposition of the thin metallic layer, you spin on photoresist. You pattern a photoresist and then you deposit the metallic layer that you want to pattern. And when you remove the photoresist, in this way, this is silicon wafer. So let's suppose that this is the photoresist. I put the photoresist, I pattern it. Okay, I spun photoresist, do the photolithography, open this area. So this is the photoresist. Now I deposit the thin layer.
A thin layer
of metallic layer. It should be metallic in case of lift off. Okay, in this way, when I remove the photoresist, so photoresist is removed, it will lift off whatever is deposited on the top of photoresist. So that's why we call it as lift off process, because it will, photoresist would be removed, at the same time the metal at the top of the photoresist would be removed. So we have only thin metallic layer at the middle. So this is the lift off process. This same thing can be done by photolithography as well. That is, if I have silicon wafer, so in photolithography, first of all you need to have the thin layer that needs to be patterned. In this case, you have photoresist and then you go for the thin layer. In this case, you have thin layer, then you want to, because you need to do etching in this case. Now I need to pattern it. So what I'll do, that I will expose these areas that I need to remove. Okay, this is my photoresist. So then I go for etching. Etching will remove the thin layer that is exposed, and at the end I remove my photoresist. So the same pattern can be achieved in both ways. So just because I was talking about the photolithography and etching, so keep in mind that lift off can also be used. Yes?
Is there a different solvent you use to remove the photoresist in case of lift off?
Sorry?
Is the solvent different for removing the photoresist?
No, no.
Then how come the metal goes away in what's on top of the resistor, not what's on?
That's why I say that there are some limitations. First of all, the thickness of the photoresist should be more than the thickness of the thin film. So if this much thick layer is removed by acetone, that removing the photoresist and developing, that is different thing, you know this thing, okay? Removing the photoresist, we usually use acetone to remove the photoresist. And developing means that only the sensitized photoresist would be actually removed by that developer. So in this case, you should be, if you have a thick layer of photoresist as compared to the aluminium or anything on the top of that, it should be metal. So when this is removed, it cannot stay in air, so it will also be removed. So because it's not actually a very, it means that the limitation is that the metallic layer that can be patterned in this case will be very thin only. If it's going to be thick enough, in that case it will become a blackened type deposition, so then even the removal of photoresist will not lift the thick layer of metallic layer up actually. So that's why if it's thin, so it means there would be actually a breakage or not a strong bonding between the pattern that we want and the pattern that we remove. So if there is a height difference, they are not connected, so that would be removed.
So only the there is a difference in the masking. Otherwise,
Yeah, there is a difference in the masking. So, but the problem is that, as I told you, it has its own benefits. It has its own benefits. In this case, you don't need to match the etchant. You don't need to think about, okay, I want to remove this thin metallic layer, which etchant I should use. You don't need to think about that, because you know whatever the metal is that will be lifted off. But it has limitations, only a thin layer, and secondly only metallic layers. So it's not a topic of discussion for today, but you will discuss in detail later on. Okay, but you know that in this case, whenever we do etching, etching is always done after photolithography. That's what I was trying to tell you guys. So after etching process, you need to make sure that there is no photoresist residues. Similarly, whenever you want to implant the dopant actually, in that case you use photoresist as the mask to that dopant implantation. So because again you are using the photoresist, so after the implanting process, that is also used for ion implantation, that is also used for the diffusion. That is a way how we diffuse the dopant. So photoresist is used as an implant mask as well. So once you're done with that, you need to make sure that implant mask is removed. Thirdly, that after post-bake, whenever you develop your photoresist, you always after developing, you always post-bake just to make sure that photoresist gets hardened. It's not etched away due to the etching. So after that step, you also concerned that if there are any residues. And the last step is actually the misaligned mask. Misaligned mask means that you need to rework on your wafer. Because if you're working on a device and you need to use more than one mask for that device, so you know that each layer of the mask, they need to be aligned with each other, and we use different types of alignment markers. Do you know this thing? That and different types of alignment markers that may be it's an alignment marker. It may be a square, but you know, as compared to a square, it gives you a better control of the alignment, because if you exactly know that the next layer alignment marker comes in here, so it means that you are controlling on all directions, in all directions. Okay, so this type of alignment markers are put on the mask actually when you know that more than one layers of photolithography process will be done in order to complete your device. So if you could not align the photolithography process properly, if there was misalignment, so it means that the next photolithography process you could not pattern it the way you wanted. So you want to rework this process. So it means due to the misalignment of the mask, you need to remove all the photoresist. So again, you need to make sure that photoresist strips are not there and you need to remove it. So these are different cases where you need to remove the photoresist. And one more thing, that when you are dealing with more than one photolithography process, in that case, while working on the second level or third level, you always keep in mind that you don't damage the underlying levels, means the first step or the second step process. So you need to be very careful while etching or while patterning the device, that whatever the etchant you are using, it is not sensitive towards the surface that I have underneath, so that you don't damage or you don't destroy the first layer of the process. So that's why you always keep in mind while working with more than one photolithography process on your device that the underlying layers, they are actually not sensitive to the steps or the etching process that you are using for the your specific desired layer. Number of photolithography cycles that can be typically done on one wafer ranges from 10 to 25, but I don't think so that usually you need that many number of cycles.
What does it mean? I mean, it's not clear. Number of
Okay,
cycles.
it means that as I told you that we can on one wafer, if you have patterned one thing, you can again spun on photoresist and go for the second cycle, and you pattern that film and you can go for the third cycle. So on the same silicon wafer, again and again spinning photoresist and spin photoresist, develop it. That is actually one cycle.
Okay, that means on the same layer.
Yeah, on the same substrate.
Same substrate.
Yes, on the same substrate you cannot do it unlimited times. So, but you can do it 10 to 25 times. Okay, and the last line says that what the cycle is. Cycle means that spinning on photoresist, and after that you develop it, means removal of photoresist. Okay, so there are different types of photoresist removal. First is the oxidizing type. In this case, commonly named piranha solution. Different ratios of this sulfuric acid and H2O2 is used. Here H2O2 is actually the oxidizing agent. That is, it oxidizes the carbon in that photoresist to form carbon dioxide, and that escapes. And that's why it's more easy to remove the photoresist if there is any photoresist residues. But as I told you before, that piranha solution cannot be used as an organic cleanup or the photoresist residual removal when you have a metallic layer. So it can only be used in case of front end of line cleaning process, not in the back end of line cleaning process. Once you have a metal on the surface, you cannot use this piranha clean because it will damage your metallic layer. In the lab we use 3:1 if you remember for this piranha clean. But mostly use, some people use 7:3 as well. That H2SO4 is 7 and H2O2 is 3. So that's why I say different ratios are used for piranha clean. But even 1:1 is used. That's also good enough. Maybe you will have to heat it up. 3:1 is very hot, and 1:1 would not be it, but you will have to heat it up to 95 to 180 centigrade before cleaning.
Also, it also takes time to cool down the distillation.
Yes, it always takes time, approximately 45 minutes, depending upon what is the concentration you use and what is the volume that is having. So depending upon your volume, the volume that we used in the lab, that it took approximately 45 minutes to cool down to level. Okay, organic strippers. Previously, there is phenol is one of the chemicals. Phenol-based chemicals were also used to remove that strippers, but lately that has been removed because the phenol disposal. The phenol disposal was very costly process actually. You know that every chemical need to be disposed through certain specific methods. We are not concerned with that. We just need to make sure that we are putting the disposal in the properly labeled containers that says that these are the chemicals that contain in that disposal, and this is the ratio of the chemicals that are in that disposal. After that, E&H department, Environmental Health Department, they actually come in and they dispose it depending upon what chemicals are in. They have their own protocol to dispose that. So phenol-based solution was having the problem with its disposal process was very costly. So it was replaced lately by N-methyl pyrrolidone. It also works well, and it can also be used to remove the organic strippers, including the photoresist residues. Dry etching. Dry etching is actually that because whatever we have used up till now, that is the wet etching. Whenever you have a chemical and you dip your wafer inside to clean the surface, so that is a wet chemical etching or a wet cleaning process. So dry etching is also used for the cleaning of the wafer surface. In that case, we use an oxygen plasma. That is in the oxygen is in ionized form, so that is used to actually etch the very thin layer of the wafer surface. So we name it as a dry etching. When we'll be discussing in etching process, then you'll come to know what are the benefits of wet etching and dry etching and what are the drawbacks. They have their own limitations and benefits over one another. But right now, dry etching is also one of the process to clean the surface, and in that case, oxygen plasma is actually very energetic oxygen ions. They strike the surface and they remove the very thin layer on the top. But of course, as the process says, it can damage your surface as well. The surface of the wafer can be damaged.
So I have a question. So for specific photoresistor, we can use any of method. Or?
Okay, not for specific photoresist. It depends upon your application. As I told you that dry etching cannot be used everywhere, but maybe depending upon if you have got high aspect ratio in there and you want to etch it and you want to be it like this. If I want to etch something and I want a pattern with the sharp edges, so this etching cannot be done with wet etching. I will have to go for dry etching. So it depends upon your application. Then you go for what process of etching you need to use. Okay, so in this case, dry etching, because it's actually the gas, it has more access to the deeper trenches. So and secondly, the wet etching mostly that is isotropic. Isotropic means that it etches vertically and laterally with the same etch rate, but dry etching etches in one direction. So even wet etching can be anisotropic, but when you will be discussing about etching, you will come to know about that. Okay, so we are talking about that dry etching. As I told you, that oxygen or fluorine can be introduced as a reactive species when we are doing the dry etching. What is the effect of oxygen and fluorine? They can increase the etching process. How they increases, and that's why you need to know about H by C ratio, F by C ratio. Right now I am not going to talk about that, but you should know that adding fluorine or oxygen, they actually affect your etch rate in dry etching.
Do they act as a catalyst?
Yes, that's why I say that the important thing is actually F by C ratio. Adding fluorine increase F by C ratio, adding oxygen decrease F by C ratio. So this is the factor that actually is affected. So when you will be talking about dry etching, you should know about what the F by C ratio, how it actually affects, and how, and you will see that F by C ratio works differently for silicon and silicon dioxide. So because this is all about the dry etching process, and today we are talking about the cleaning, not the dry etching, so I don't want to get into details. But when you will be talking about dry etching, you should put up the question about F by C. Okay, so as I already have taught that the plasma can damage the surface and the etch rate is high, and when we introduce these agents, actually they react with the surface, and after that through the vacuum they are removed from that chamber. Here again we are talking about the photoresist removal by etch chemistry, etch time, implant energy, and dose. So we are talking about the dry etching again. In the dry etching, the time, for how much time you are putting your device inside the chamber, the dose means that what is the concentration of your etchant, actually the etching agent. So what is the concentration or what is the dose of the gas that you are introducing in that chamber? What is the implant energy of that? Means how energetic, how fastly they are reacting with the surface, and what is the etch chemistry as well. Because maybe for etching one material, you may have more than 2 to 3 gases there available, but one gas reacts fastly than the other. So etch rate of every gas is different from the other. So that they are the 3 to 4 parameters that you need to keep in mind when you are working with the dry etching process. The time, the concentration, the etch rate, and the energy or
RF power.
yes, that is the power. So but you have good controls, and that is very simple process, dry etching process. You have controls that these are the gases that you want to introduce, and this is the concentration or the power of this gas. Even you can use more than one gases, a mixture of 2 gases, to move any surface while dry etching process. Okay, so because we are basically discussing about the cleanup process, that was just dry etching is also one of the process that is used to clean the surface. As I told you, that oxygen plasma is very commonly known process to clean the wafer surface. The other ways how we can clean the surface, they are named as vibrational method. We can use the ultrasonic or the megasonic waves. The ultrasonic waves, how we do this thing, that in a liquid it may be DI water or it may be the H2O2 liquid. So in that liquid we produce the high energy sound waves actually. Those waves, due to those waves, what happens that because they are the waves, so what happens that bubbles, they form and immediately they collapse. So when the bubble collapse, you get a liquid free space or cavity. So when the bubble forms and immediately it actually collapses, no sooner did it collapse, there would be a cavity. Okay, so in this way when you have the vibrations, so you form and you collapse the bubbles, named as the cavitation bubble. So that cavitation is actually the process that makes the surface of the wafer clean. What we do that we don't touch the surface. Keep in mind that liquid is there. In this case, we don't have any brush or we don't have anything that actually touches that is in contact with the surface of the wafer, but just the wafer is inside a liquid. It may be DI water, it may be H2O2 or any other liquid. In that liquid we produce those sound waves, and due to those sound waves the cavitation effect comes into account, and the surface of the wafer, the particles on the surface of the wafer, they actually got displaced, and because it is moving, so it can clean the wafer surface. But you know this thing that due to this cavitational shock, because it's just like a shock, because it collapsed suddenly, so it works like a shock. Due to this cavitation shock, the wafer surface can be damaged as well. So just to avoid this cavitation shock, what we do, that we go to higher frequencies. We go to megasonic frequencies. At high frequencies, we are not providing enough time for the bubble to get collapsed. So the bubble does not get enough time to get collapsed because the frequency is high. So that's why those shocks do not come into account, and we can avoid those. But the rest of the process is the same. That the liquid that is used, that may be DI water, that may be SC1 or SC2, they are actually the standard cleanup process, one standard cleanup process 2, and they are the parts of RCA process. So it means it may be any chemical solution, the liquid, and after that you give some higher waves than the ultrasonic waves, named as the megasonic.
So questions, can you specify what particle is it? So like
what particles it removes actually?
Right.
It removes actually the dust particles, or it may be any traces of some thin films on the surface. But if you have some, even if you have some metallic ions on the surface, but not heavy metals, if you have some metallic ions, that can also be removed. So anything, any particles on the surface, that mostly it's the dust particles that are introduced due to the process steps, or it may be the traces of the thin layers that if you have a thin layer pattern and it breaks at some point, after breaking the thin layer, it may be deposited on the surface. It may get stick on the surface.
Bombardment, right?
Due to any damage, that because the thin layer can, if you have patterned thin layer, if you have this wafer, let's suppose I'm talking about the top view. It's a thin layer, a U-shaped thin layer. So maybe it breaks at here. So this part is broken, and that broken part may stay on the surface. So that's good name as the remaining traces of the thin layer. That is the parts of the thin layer that are introduced on the surface due to breaking of the thin layer. So that are removed actually. Okay, after vibrational process, there is one other process named as the scrubber. So in this case, water or any other liquid that is supplied to the wafer surface, and there are brushes that are made of PVA, that is polyvinyl alcohol. That PVA brushes are used to push the water or the other liquid along the surface of the wafer. So in this case, again keep in mind that though the name looks like scrubber, means it scrubs the surface, but it does not. It does not it does not contact the surface of the wafer. The brush does not contact the surface, but it's very close to the surface, and it exerts some pressure by the liquid between the brush and the surface. So it's just the pressure, it's just introducing some pressure, and it also causes the movement of the liquid along the wafer surface from one point to the other. But it's not contacting the surface. That is the one point that I want to keep you guys to keep in mind.
CMP again?
Sorry?
CMP?
CMP.
Oh, CMP. CMP is actually chemical mechanical polishing. We call it as chemical mechanical polishing or chemical mechanical planarization. At the end of the fabrication process, you go for CMP. That is at last you go for CMP. So metallization and CMP, they always come at the end of a process. If you remember last time, the slides we were talking about, in that case there was a step CMP, the chemical mechanical polishing, when we deposit in the trenches, when we deposit oxide, and after that we do chemical mechanical planarization, so we remove that oxide layer. Remember, that is shallow trench oxidation. In this shallow trench oxidation, we talked about CMP. Okay, so why we use PVA? PVA because they are very soft and elastic material, and they are good to exert some pressure, and they have some flexibility as well. So that's why PVA has been considered as a good material for making those brushes along the surface of the wafer. Wafer rinsing and drying. So you know, always after cleaning we go for rinsing the wafer in DI water, and then we blow it dry with nitrogen. So far as why we rinse the wafer in DI water, because after that particular chemical has done its job, we want that chemicals to be removed from the wafer surface. We don't want that chemical to be on the surface, so that's why we rinse it in DI water. So DI water is deionized water, very high resistant water, so that does not have any contamination, so that removes that chemical. For example, after piranha cleanup, if you rinse it in DI water, so any sulfuric acid or hydrogen peroxide chemical that was on the wafer surface, that is removed due to this rinsing process. There are different ways how the rinsing can be done. First of all, one is named as overflow rinse. In this case, what happens that you have a tank of DI water and you put your wafers loaded in just like we did in the lab, but that is not actually the designated tank. We use beaker as a tank of DI water, but in the fabs you have the tanks of DI water. At the bottom the water actually keeps on going out of the chamber, and on the top the water comes in. So in that case, why we do so? Because we don't want those contaminations moved by the DI water after in the rinsing process to get stick with the wafer again if they stay in the DI water. So that's why in that, as the name shows, overflow rinse, that we have the chamber, we dip the wafers in, and after that that DI water is overflowing, so the new water is coming in, and from the bottom of the chamber the water is going out. In order to increase the flow process or make it more directional, we mostly use the nitrogen. Nitrogen bubbles are introduced from the bottom, so in that case it makes the process better. So we can introduce the nitrogen in that as well. The second process is dump rinse. This is also very similar to the overflow rinse process, with a minute difference. First of all, that you don't fill up the chamber, you don't fill up the chamber of the DI water before you put your wafers. What you do that you put your wafer and you start spraying DI water from the top on the surface of silicon wafer. So you start spraying, at the same time you start introducing DI water from the bottom of that chamber, actually of that what I would say, that enclosed part where we are actually having our DI, the wafers. So why we call it as dump rinse, as the name shows, that the bottom of that chamber, that is actually a fake bottom, because when it actually fills up, that bottom is removed and all the water is dumped to the drainage process, and again it starts putting up new water, and so it's different from the overflow rinse in the way that we spray, and after that it's not continuously getting out, it's dumped at one time. When it's filled, and the bottom is removed and the water is dumped, and then again bottom comes in and again the process starts. So we can repeat this process.
What we did in our lab, that is dump rinse.
Sorry?
What we did in the lab, that is.
Oh no, we did not did the.
No, we just clean with DI water. So what?
Actually, what we did in the lab, that was because these are the rinse dedicated process. They are in the fab. We don't have in the fab that thing. So we rinse it manually actually. So that's why, if you remember that after taking it out from that DI water, I asked you guys to rinse it in the DI water manually, because we need the fresh DI water to clean the surface. After one chemical process, the cleaning process, when you put it in DI water, some of the contamination would still be inside that DI water. So that's why we need to put up or flow the new DI water on the surface of the wafer.
So we are doing none of this process.
Yeah, we are doing. But I just want to let you know that what are the different processes. The third thing is various spray rinse configuration. This is also done. It's not. This is what usually is done in the clean room at universities as well. But in our university we don't have it. That is, in order to rinse the wafer and blow it dry with nitrogen, you don't do it manually. You have the dryer, and that are actually the spin rinse dryer. So you put the wafer inside, the DI water is sprayed on the wafer surface, and at that time it's rotating as well. And after that, hot nitrogen is actually blown on the surface, and at the same time it's rotating at high speed. So due to the rotation, the water splits up, so it makes the process even more fast. So that is more safe because you are not holding it with hand, and more safe and more cost effective as well, because you are actually spraying the DA water on the surface, and more efficient. But we don't have that. We call it as spin rinse dryer, SRD, I guess, something like that. So spin rinse dryer, we don't have it here, but I have been working at UTD Clean Room, so they have those spin rinse dryers. Okay, so for the drying process, the first thing is again spin dryers that I talked about, that is safe and cost effective, and it needs ionized nitrogen flow into drying chamber to reduce charging. Why we need ionized nitrogen gas while drying it? Okay, so when it actually rotates at high speed, and nitrogen is blown on the surface, after that when you take it out, because that is the hot nitrogen, when you take it out of that chamber and you expose it to the atmosphere, it's very likely to get reaction with this air, because it has got the charge, so it can attract the particles. It gets charged on its surface. So that's why, so that it does not get charged, later on the scientists introduced the ionized nitrogen while rinsing it in that spin dry. So ionized gas actually restricts the wafer to get charged. If you are not using the ionized nitrogen gas, in that case when you take it out, it will be charged, and the charged surface always attracts the particles towards its surface. So to block that charge, we use the ionized nitrogen gas. Okay, so second is IPA vapor dry. In this case, what happens that what we do that when you have your wafer in DA water, the wafer is still wet, and you put it inside an environment that is filled with IPA, isopropyl alcohol in vapor phase. Okay, so what happens that, and that is also at approximately 80 degrees centigrade, I believe, that IPA, and at that temperature what happens that there is an IPA coating on the surface, so water is replaced by IPA. In that environment, when you have the wet wafer inside IPA in vapor phase, so IPA gets on the surface and water is removed. Then you take that IPA coated wafer outside, so you know that IPA is actually an organic solvent, so that is very volatile, that evaporates very fastly. So when you take out the IPA coated wafer, it evaporates very fastly, so that is another way to get the wafer dry. And when you take it out, it evaporates very fastly. At the same time, you blow the nitrogen on the surface as well, so that you make sure that there is no water residue on the surface. The last drying process is named as Mayagonin dry. He was scientist who actually developed this process. What he did, that if you have the wafer that is inside the DA water and you want to get it dry, so if you pull the wafer at a very slow speed at 1 to 2 millimeter per second, only 1 to 2 millimeter per second, so the wafer was inside the DA water, and the outer environment was IPA plus nitrogen. The outer environment was IPA, the chamber, the ambient environment was IPA plus nitrogen. So what happens that when you take it very slow, the meniscus between the IPA environment and the water, there should be, because when it's taking out, there should always be a meniscus between the IPA and the water. So at that meniscus, the IPA gets absorbed at very thin layer, so there is a gradient between the IPA concentration at that meniscus and in the surface of the water. So due to that, due to that IPA, due to that gradient, there is actually surface tension gradient, and because there is a gradient, when you pull the wafer outside, the water actually pulls the water towards its bulk volume instead of letting it go with the wafer. So that is, he was actually, I think so, an intelligent scientist. So he gave this idea. So due to his name was Maragit, so Maragoni, so this process was named on his name. So it's also, though it's an time consuming because it's slow, you need to take it very slowly, but it gives you another way to get your wafer dry. So due to that gradient of the surface tension, because IPA is at higher concentration at the top and lower concentration at the bottom, so that's why the water pulls the water towards its volume and does not let the water go with the wafer surface. Watermarks, as I told you that if you remember that when you were taking your wafer out of that quartz board, it was not, if you blow it dry, it was not at all very clean, the surface was not clean. You were supposed to rinse it dry in clean DA water. So that's why if the water is automatically dried on the surface of the wafer, so you get the water marks on the surface, and that is also one of the contamination. So you don't want the water marks, you need to be careful that water marks are never there. Water marks can be there due to many reasons, but the exact reason why the water marks are there, that has not been completely understood what is the phenomena behind. But some people say that it's due to there may be some pits on the surface and water actually stays in there, and some says that water actually etches away that part where it stays. So, but watermarks is one of the contamination, and you always consider that there should be no watermark if you want your wafer to be considered as a clean surface. Wafer drying, I believe that we have talked about this thing. Spin rinse dryer, on the left side you can see that it spins, and this is what Maragoni dryer I was talking you about, that here IPA and water, so there should always be an interface between IPA environment and the water, and at this interface IPA concentration is more, so that's why there comes in a stress or a surface tension. So due to that, the water always tries to pull the water towards its bulk volume, and the wafer that is getting out at very high speed, that does not have any kind of water on it. Okay, so contact angle and wetting behavior. Contact angle is, do you know about the contact angle? Did you hear about that? The contact angle. Why we use the contact angle usually in research? Why do we need the contact angle?
Adhesion. It's related with adhesion.
Okay. So whenever you need to make sure, or you want to check it out in the research, you don't know that maybe I am depositing some polymer. I deposit the polymer, and after that I want to check it out whether this polymer is hydrophilic or hydrophobic. So in order to confirm the hydrophobicity or hydrophilicity of the surface or of any material, you go for the contact angle measurement. So contact angle measurement tells you about the hydrophobic nature or the hydrophilic nature. So as you can see that in case of in A, the hydrophobic nature, the angle theta, that should be greater than 90. Why it should be so? Because if I have a surface and I get any polymer deposited on the surface of the wafer, this is a polymer. If this polymer is hydrophobic, for example, and there is a drop of water, so drop of water, because it's hydrophobic, that water does not want to get in contact with the surface. It tries to make as less contact with the surface as possible, so it tries to contract within itself. So it tries to make less contact with the surface. So it will make like this. If I want to find this angle that the water makes with the surface, and this angle is greater than 90. If this angle is greater than 90, means it's actually hydrophobic, because it does not want to have greater contact with the surface. It tries to get itself away from the surface, because in this case the water has tried its best to get itself away from the surface. And if this surface were a hydrophilic surface, in that case the water loves to get in contact with the surface, and the same droplet should have formed this shape, because now it gets in contact with the surface.
So what's the reasons behind? What are the reasons behind to be hydrophobic or hydrophilic? What?
The water is not hydrophilic or hydrophobic. It's actually the
nature.
surface.
Surface.
Water is the same. Hydrophilic means that something that that has attraction towards water, and hydrophobic means that something that actually hates to get in contact with the water. So that's why if something is hydrophobic, you cannot get it dissolved in water.
So it depends on the property of surface.
It depends upon the property of the material. So hydrophobic or hydrophilic, this is the material property, not the water property. But that material property is related to water. Means if something is eager to get in contact with water, so that material is hydrophilic. And if something is not having any affection with water, so it means that is hydrophobic. And in research, we always want to have the hydrophilic surface. Yes.
Is it only for water or other liquids as well?
Anything that contains hydrogen actually, but we always test it with water.
And why would you want to know whether it's in order to rinse it or?
No, that's why I say that in research work, let's suppose that I want this surface to grow my cells. I want this surface to grow a cell. So cells are the living animals. Cells cannot be grown on a hydrophobic surface. Secondly, another example I can give you, that I have a nanopore, for example. Nanopore, you know that that's a very small hole, and I want to run an experiment. So I coated my nanopore from the internal side with a polymer. In that case, I want that liquid to go through. The liquid may be there should be water containing some salt, that is to develop ionic concentration. So that liquid, that water, if that material is hydrophobic, I will never be able to get that water pass through that pore, because it would throw the water away from itself. It will show always a resistance to the water to pass through, because it's very small. It's already having some resistance to get anything to pass through because of very small hole. So I need to make sure that the polymer that I am depositing on the pore, that needs to be hydrophilic. In that case, I can use that polymer in my experiment, otherwise I cannot use. Otherwise you cannot run the experiment, because if that polymer is hydrophobic, in that case it names as wetting of the pore. Do you know what wetting? So in research we use this term, wetting of the pore. So pore will never be wetted until and unless it has hydrophilic surface. So if it is hydrophobic, you cannot get your pore wet. Get your pore wet means that water can pass through.
So it's only affinity to hydrogen, not the oxygen of the.
Hydrophilic and hydrophobic, mostly they are considered with respect to water, but you can, I exactly don't know that what is the hydrophobic interrelated properties, what should hydrophobic, I know, but they love water, they hate water. So, but as the name shows, they should be hydrophobic, means phobic from hydrogen, so that's why I think so it should be from the love for hydrogen or hate for hydrogen. But you can check it out that what other alternatives can be used instead of water. But for measuring the contact angle, we always use water. Okay. So particle counter at the last, in order to make sure that your wafer surface is clean or not clean, we have certain equipment that is used to count your particles on the wafer surface, that how many particles or how many contamination particles are on the surface. For that case, what we do, if we have got an unpatterned wafer surface, we use an optical laser that is striking on the surface at right angle, that is vertically it strikes the surface. If the surface is very clean, if there is no particle at that point, so actually you scan your wafer, the complete wafer is scanned, so with that laser. So whenever there is no particle on the surface, it means that the laser will be coming back vertically in the same angle, at 90 angle. So at that right angle, it will come back and it will not be detected by the detector. Whenever there is some particle, a contamination of any type, due to that particle, the laser will not be coming back at right angle, it will get reflected. Okay, so when it gets scattered from that particle, it is detected by the detector and says here is some particle or some contamination here, the wafer is not neat and clean. So you know that the laser diameter, that is very small, so you can actually, while scanning, you can actually calculate how many particles are there on the surface. And if you have a patterned wafer, in that case, in patterned wafer means you already have a rough surface. You don't have a smooth surface. So when you already have a rough surface, so in that case, the phenomena of vertically hitting with the vertically hitting with the laser, and after that you expect to be it back at right angle, that will not work for a rough surface, because the rough surface means that it will never come back vertically. So even if it's the pattern, it's not the contamination, but you will feel like that there are particles and contamination all over the surface. So you need to go for another technique for the patterned surface or the rough surface. In that case, what you need to do, that you don't strike the laser at right angle, you strike it at some obliquely, at some angle, and at that angle, when it strikes that pattern, it comes back, and again it's received by the detector at some oblique angle, and after receiving that scattered beam, it compares with already known scattered beam, that whether it's the pattern or it's some other contaminating particle. So if there was only pattern, how it should be, it already had that known pattern in memory. So when it compares with that, if it's scattering the same way, it means it's not the particle, it's actually the pattern. So you strike it at some angle instead of vertically. So that is the way how we actually calculate the number of particles. Okay, so it was something about cleaning. Now we are going to talk about the diffusion. Just like oxidation, diffusion is also one of the very important processes. Actually, there are 5 basic processes in silicon IC fabrication technology. Out of those 5, this diffusion, or we call it as ion implantation, actually we should call it as doping. So doping is one of those 5 basic processes: oxidation, doping, etching, photolithography, and metallization. So these are 5 steps. So oxidation, we have talked about. Photolithography, I believe we'll be discussing later. So doping is also one of the very important parameters, because doping actually affects all the other processes in your fabrication, fabricating the device. So doping is done by 2 techniques, either by diffusion or either by ion implantation. That you bombard the ions and you diffuse your dopant, or you actually go for the diffusion process. So these are the 2 methods how you actually introduce that dopant concentration inside your surface or silicon wafer. We are not going to talk about ion implantation today. We'll be talking about diffusion, but you should know that that can also be used to introduce the dopant concentration. But Both of these again should have their own benefits and drawbacks. So you should know what is the benefit of diffusion, what is the benefit of ion implantation, where ion implantation is better and where this diffusion is better. So because when you know the comparison of all the available methods for some process, then you can think about that for your device, for your project, what you are working on, which process should be used. As I told you that if I know that in my device I have a patterns like this, so I will know that okay, I need reactive ion etching or dry etching. I would not be using an isotropic wet etching. And similarly, this diffusion and ion implantation, they also have their own benefits, but I am not going to talk about the comparison, because once we talk about ion implantation, you will automatically come to know about the comparison. In diffusion, what we are going to discuss for today, first of all, the mathematical equation for diffusion that was given by Fick's. If there is Fick's first equation and Fick's second equation, first law and second law, and we can find out the solution by applying certain boundary conditions, and that solution can be used as an equation to find out the diffusion or the dopant concentration at any depth. Okay, that Fick's equation, the mathematical equation, we will talk about two things, that is pre-deposition and driving. Pre-deposition and driving, these will be two things. After that, we will be talking about defects and dopant diffusion. Then we will talk about diffusion in polysilicon and silicon dioxide. Actually, these are just the names of the techniques that we'll be discussing later on. Then there is some anomalous diffusion effects. It means that the Fick's equation, the equation that we will drive in certain conditions, you don't get the right answer. So it means that that equation does not work well. There are certain other parameters that actually affect the diffusion. We call it as anomalies in that diffusion process. So we will talk about those different anomalies as well. Diffusion metrology, at the last we will talk about that how to find out how to measure actually the diffusion in your surface of the wafer. In diffusion metrology, the methods that we use, first thing, you can measure the sheet resistance, because greater the dopant, greater will the sheet resistance or the lesser? Greater the dopant concentration, less resistance. That's very obvious. So greater the dopant concentration, lesser would be the sheet resistance. This is what we will be doing in the second experiment in our lab. That we will diffuse the wafer in the diffusion furnace, and after every 10 to 15 minutes we will find out the sheet resistance, and you will see that the sheet resistance goes on decreasing, means we are activating more and more and more of the dopant atoms.
Why the name is sheet resistance?
Its name is sheet resistance because sheet resistance is defined as, because it's the resistance of a square sheet. Is defined as the resistance of a, if you have a square of 1 centimeter by 1 centimeter and you find out what is the resistance of this sheet, it should have some thickness as well. So that's named as sheet resistance.
But thickness is very less.
I believe you know about resistivity at least.
Yeah.
Do you know about resistivity?
Yes.
Defined by rho. This parameter is known, okay. Then sheet resistance RS is always equal to resistivity by thickness of the thin film. So if you know the resistivity and you divide it by the thickness of that thin film we are talking about, so you calculate what is the sheet resistance. And other two methods that are used to find out the diffusion value, that is actually SRP, that is spreading resistance profile, SIMS, that is secondary ion mass spectroscopy. So all these topics will be discussing later on. Introduction to diffusion. What is the diffusion? As I told you that the movement of the dopant inside your wafer, that is actually the diffusion. the movement of chemical constituent due to the constituent gradient. If you know that in general term, what we call diffusion, what is diffusion actually in general term?
Higher concentration.
Yes, everything that moves from higher concentration to lower concentration. And just like this smell, the perfume, if I put some perfume here, so through the air it actually diffuses. That names a diffusion because it moves from higher concentration to lower concentration. So similarly, this is what happens, that we introduce a high concentration on the surface, and after that it moves from high concentration to lower concentration at high temperature. So we say that we are activating our diffusing element. Okay, so as I told you that at high temperatures, we actually gets our diffusion to get into the wafer more and more as we keep at high temperature for more and more time. Okay, the upper limit of that diffusion, that can be actually, the maximum is the solid solubility of that dopant in that layer. The solid solubility, you cannot in the upper, there is an upper limit. You cannot put maximum unlimited dopant in that specific structure. There is an upper limit, and that is actually, like for example, boron, the solid solubility of boron in silicon, that is the maximum dopant of boron that you can introduce in silicon. So as the graph show, that higher the temperature, higher would be the dopant. But at the same time, it also depends what type of dopant you are using. Means boron has got a different solid solubility, phosphorus has got even more solid solubility than that, and aluminium has got very less solid solubility. So that's why aluminium cannot cross this limit at 1300 degrees centigrade. But you know, at this point, boron has much higher than that. So the solid solubility of that dopant is an important factor. Okay, because we don't have that much time, that we'll be discussing the mathematics of diffusion, but I can just give you a brief idea that in diffusion, first of all, what you do, that you have, there are two steps: pre-deposition and driving. In pre-deposition, what you do, that you pre-deposition, as the name shows, that you put your dopant on the surface. On the surface, you introduce your dopant. You can do it in any way. You put it in any gaseous environment that contains that particular dopant in that gas, or what you can do, you can spin on dopant on the surface. That is solid, and you can spin on dopant. This is what we'll be doing. We'll be doing spin on phosphorus dopant on the surface, and this is pre-deposition. So on the surface, the surface concentration is always constant. In pre-deposition, the surface concentration is constant. It's constant means that depending upon the time, if this is T1, this is T2, and this is T3, and T3 is greater than T2 is greater than T1. Okay, so higher the time, the greater would be the depth of that, but the surface concentration is constant, because because you have unlimited source, not unlimited surface concentration. This is constant, not unlimited. This is one thing that people make mistake. When I say unlimited source, it means that when one atom diffuses into the other atom is replaced by that from the source. Okay, so you always have the constant concentration on the surface. Whenever you move 2, you put 2. Whenever 3 are diffused into, 3 are added as well. So this is named that this is a pre-deposition. In pre-deposition, the surface concentration is constant. After you have the surface concentration constant, this was the pre-deposition. You'll be discussing this thing in next lecture. Actually, I'm just giving you an idea. Then comes the drive-in. In drive-in, what you do, just you put your wafer at high temperature. At high temperature, you have constant concentration on the surface, and after that, it tries to go deeper and deeper and deeper. So initially, let's suppose you started with this, that it was only on the surface, it was only on the surface. This was only the thickness that was having that dopant. It was only on the surface. After some time, at high temperature, it moved up to X2. But the surface concentration, you can see it has decreased because now you don't have the source. Whatever you had, that is constant. After some more time, it goes even deeper. So the important thing is here that in every case, the area under the curve is always constant, because the area under the curve is actually showing the total number of dopant molecules, and that is constant in driving. So in driving, the area under that curve would always be constant, just the matrix that from the surface dopant is moving into that wafer. So this is the driving, but this will be discussed in detail in the next lecture. Hopefully Dr. Bal will be here, so he'll be taking the next lecture, and he'll be starting from driving and pre-deposition. Okay, so that's all for today. If you have any question, you can ask me. Nothing? Okay. Hope to see half of you tomorrow in the lab again. And in the next lecture, Dr. Bal will be back. One thing about the diffusion that I want to mention, when we say in driving process, we activate our dopant. So some people don't know what do we mean by activating a dopant. Because if you have, if you introduce a dopant and it's interstitial means that the silicon atom, this is silicon and this is silicon. It is sharing 4 oxygen atoms. It is sharing by, it has 4 outer shell atoms, so it is shared by 4 other atoms because that is covalently bonded. So if I have, so it will be covalently bonded on 4 sides. It has 4. If I have a boron atom here, boron has 3 outer shell atoms. If I have it here, I have it in the layer, but it's not replaced by one of the silicon, so it's not activated. It's interstitial. It's of no use for me. It's of no use at this time, because it will be of use to me when it replaces any one of these. When it gets replaced by silicon, it makes it interstitial, it replaces itself by it. So it means now there would be, it has 3 atoms, so there will be 1 vacancy available, and that vacancy is actually increasing my current capability or decreasing my resistance. So activating means making my dopant beneficial for me, making my dopant replaced by the original atom. So that is actually you activate a high temperature. Okay, so that was just one term, because usually